Awesome. So yeah, like Tyler said, it's our last block and it's our last review session. So we're just going to go over everything in block 4 and then open up to questions from everything. So let me get screen sharing going. There we go. And these will get sent out immediately after the review. But block 4, so it was all about optics. And I sort of like this block because, well, first of all, let's admire this dabbing emoji, because we made it pretty far in the course, and this material is not easy by any stretch of the imagination. So good job, everyone, for making it this far. That's meant with complete sincerity. But the reason why I like block 4 is because it's where everything comes together really nicely, and the beauty of E&M really shines. So let's just briefly remind ourselves of what we did to get to where we are now. We started this course in electrostatics, and that was the study of stationary charges. A stationary charge just by itself sets up an electric field according to Coulomb's law, which states that the differential electric field is K dq over r cubed times the r vector. And we also learned about Gauss's law, which is our first Maxwell equation, which asserted that the electric flux through a closed surface is proportional to the charge that it enclosed. So if I had some positive point charge, that was where I could draw a Gaussian surface around that point charge. And then the electric flux through that surface would be proportional to the amount of charge enclosed. So if I had more charge, I would have more electric field lines coming out of this gray surface. And we learned about a quantity known as voltage or electric potential, which is basically just a scalar way of getting to the same thing as fields. It carries the same information as electric fields, except it's a scalar, so it's a little bit easier to deal with in some cases. So after electrostatics, we also got to magnetostatics in block 3. And the analogy that we make is that where stationary charges create electric fields, that was electrostatics, moving charges, currents, create magnetic fields. So where we had the Coulomb's law to find what the electric field is from a stationary charge, we have the Biot-Savart law to tell us what the magnetic field from a collection of moving charges is, from a steady current. And it's that integral expression, mu naught I dl cross r over 4 pi r cubed. The reason why magnetics tends to be a little bit harder is because you have to consider a little bit more dimensions, because you have these cross products with dl's and you're crossing them with r, where we didn't have any sort of cross products in Coulomb's law. But on the whole, the Biot-Savart law is very analogous to Coulomb's law. We also have Ampere's law, which is sort of analogous to Gauss's law, because Gauss's law told us about stationary charges within a Gaussian surface that could tell us the flux coming out of that surface. Ampere's law was similar. That's where we had steady currents, rather. If I just had a steady current, I could, instead of enclosing it with a surface, I would enclose it with an Amperian loop. And then that would allow me to solve for the B field on that loop. So here's our nice parallel that we sort of made so far. In electrostatics, we had stationary charges, which we can use Coulomb's law to figure out what that electric field is, and then that gave us Gauss's law. With magnetostatics, we had moving charges, or steady currents. That was the Biot-Savart law, which gave us the magnetic fields, and then we can derive from that Ampere's law. One key distinction, though, between electric and magnetic fields is that there's no such thing as a magnetic monopole. And what do I mean by that? Well, with electric fields, we can have just a positive point charge sitting by itself, and it's going to create a field. So we have field lines pointing out and about, sort of like that. There is no such thing as a magnetic charge where we can have just some sort of positive magnetic charge and have, instead of electric field lines pointing out, we could have magnetic fields pointing out. No such thing exists, at least not in nature. We haven't found one yet. Maybe it does. But for our purposes, it doesn't. Where magnetic fields come from, if you just see like a bar magnet, for instance, where we would have a north pole and a south pole, the magnetic fields of that bar magnet loop in around itself. So there is no way I can enclose it with a oh, there's chat questions. Sorry, not for
You're
me.
good, Nick. I got them all.
Okay, cool. There's no way I can enclose a Gaussian surface around any of those magnetic field lines and have a non-zero amount of field lines coming out. No matter how I enclose the field lines of a magnetic field, whatever field lines go out of my surface have to go back in. And that's the statement right here. We didn't use this equation too much, but it's just important to keep in the back of our head that no matter what kind of closed surface I have, the net magnetic flux coming out of that surface is always going to be zero. But that being said, there still can be a non-zero magnetic flux through an open surface. And that was all of what we did Faraday's law with. Because Faraday's law said that whenever we have some sort of loop, and it doesn't matter what kind of loop, and the magnetic flux through that loop is changing. So maybe this B field is getting bigger, or maybe I'm moving the loop so it moves from a region where there is a magnetic field to one where there isn't. But whenever the magnetic field through a loop is changing, there's going to be an induced voltage inside that loop. And Faraday's law is also sometimes written in this integral form, but I think this is a little bit scary and we don't have to deal with it. All we have to deal with is the EMF is the negative derivative of the magnetic flux. And the negative, again, it just comes from Lenz's law, which states that nature doesn't like change or changes in flux. So any induced effects will be in the opposite direction of whatever caused them. Cool. So this is pretty much brings us to the end of block 3, because what we have so far are 4 Maxwell equations. You have Gauss's law for magnetism, Faraday's law, which is now fully complete, and Ampere's law. And this is what Maxwell was looking at when he did his work in the middle of the 1800s. But there was an issue with the 4th equation. There was an issue with Ampere's law. And here's the issue. So as we have it, Ampere's law is the integral of B dot dl equals mu naught times the current enclosed. So let's suppose I'm charging a capacitor with this battery. So I have current flowing here, and this is becoming a positive plate, and then this is a negative plate. And I want to figure out what the magnetic field is on this Amperian loop. So I want to figure out what kind of a B field do I have here. So the first step in any Ampere's law problem is to just draw an Amperian loop. So that's done. But now I have to figure out what's the current enclosed, or what's the current going through that Amperian loop? Well, we could just say that the current going through the loop is whatever current is straight up going through the loop. But if you think about how Ampere's law is derived, it comes from Stokes' theorem. And Stokes' theorem basically relates what goes on the boundary of a surface to some surface that has that boundary as its edge. So more precisely, it's not just how much current is going through the Amperian loop, it's how much current is piercing a surface that has that loop for a boundary. It's a subtle distinction, but it's important. So we could just say that the surface that we're considering is just the plane, or the circle that defines the loop. And then the current enclosed is not too tricky, it's just the I through. But what if we do something a little bit more complicated? What if we sort of, like, imagine this is, I dip this in soap and now I'm blowing a bubble. And I blew a bubble, so now instead of having like a disk for my surface, I have a balloon, or like a bubble shaped surface. The current is still going along this path, but it's not piercing the surface anymore. It's not piercing my balloon shaped surface. So what I'd have to conclude is that my I naught is 0 and that I don't have any magnetic field. But that's obviously not true, because if I have this surface, I do have current going through and I do have a magnetic field. So something's wrong here. And the way Maxwell fixed Ampere's law was by introducing a displacement current term into Ampere's law. And that fixes the issue, because in one case, you no longer have here with the balloon shaped surface, we have a current going through the loop, but we don't have a current piercing the surface, but we do have an electric field. So we do have something right here. Whereas in the other case, if I just have a disk for my surface, I do have current piercing the surface, but I don't have any electric field. So this term is 0. So that fixes that conundrum. And it's a misleading name because displacement current really doesn't have too much to do with current, other than the fact that it shares units, because it's really nothing about moving charges. That's what current is. It's just the movement of charges. Displacement current is just a way of fixing Ampere's law. But it does have a nice aesthetic appeal, because Faraday's law told us that a changing magnetic field is going to induce an electric field. And Ampere's law can now tell us the exact same thing, but in reverse. A changing electric field right here, dt, d phi dt, so something's changing with respect to time, has to induce a magnetic field right here. So that way we have a nice interplay between electric and magnetic fields. And this brings us to classical electrodynamics. So we have all 4 of the Maxwell equations. They're completely finished. And together with the Lorentz force law, this builds up the entire theoretical content of classical electrodynamics. So this whole entire course, literally everything we've done up to this point, has been working out the details of these equations. Nothing more. Every single equation on your equation sheet can be derived from these, which I think is pretty cool. Cool. So now let's move on to topic 4b, which is all about electromagnetic waves. And I guess if you think about waves, no one really knows what they are, because you can say that's a wave. Maybe something like that if it's moving along there. But how do you quantify that? What can you say has to be constant always? Because you can also say something like that shape is a wave. It's not an easy question, is sort of what I'm getting at. But a nice way to treat waves is with the so-called wave equation. And it sort of looks scary. It's a partial differential equation, so don't worry about solving it too much. Just remember for now that the solutions to the wave equation that we want to care about are sinusoidal waves. And in fact, here's the most general form of a sinusoidal wave. For those of you who had different DiffEq so far, or if you haven't, you'll probably have it soon. I strongly recommend, just for your own satisfaction, straight up taking 2 derivatives of this function with respect to z, and then 2 derivatives with respect to t, and see that they're equal to each other with this constant factor. It's a pretty satisfying to look at, but basically all that is to say is that this solution right here is a solution to the wave equation. And those are the waves that we're most concerned about in E&M, because that's what light is. And let's just get some terminology out of the way. So A is the amplitude of the wave. That's basically how high it is. The argument of the cosine, so everything in these square brackets, let me change colors. In these square brackets, that's known as the phase, and delta is the phase constant, this lowercase delta. We usually don't have to worry about delta. It's just a way of shifting the wave sort of back and forth horizontally. If I made delta bigger or smaller, the wave would move back or forth along the z-axis. And finally, k is the wave number. It's related to the wavelength via this equation. And the way I sort of like to remember it is when z moves over by 2 pi over k, the cosine does 1 complete cycle. There's usually an easier way to express waves, though, because I find this form a little bit daunting. What I like to do, and what we do most of the time in this class, is instead consider the frequency, which is just 1 over the period of the wave. And then once we have the frequency, we can calculate the angular frequency, 2 pi times f. And then our wave equation just simplifies to this. This is something that's probably worth committing to memory because it comes up again and again in block 4 problems. But a wave is basically just its amplitude times a cosine, kz, or I guess this can be x, y, or z, just some spatial term, minus omega t. And we usually don't have to worry about the delta, but that's just sort of an offset if we need it. Cool. Chat questions. Is the general form on the equation sheet? That is a great question. I have the equation sheet pulled up. I don't quite remember. It's not. You have the omega definition on your equation sheet and you have K. So what I would do is, if you want to remember the general form of the wave equation or of a wave, it's G is equal to some amplitude times the cosine. And then sort of like the trick I use in my head is whatever I feed into my cosine can't have any units. So K has units of 1/meters and Z has units of meters or X, whatever. And omega has units of 1/t and T has units of time. So whatever I feed into here has to be unitless in the end. That's sort of how I remember it, but I don't know, Tyler, if you have any better ways of remembering the general form. It's just this. Cool, great question. There's another one. Yeah. Cool. All right, so now let's wrap it back to E&M. So if we scroll back up a little bit, we got to Maxwell's equations. And those are cool and all, but let's consider the special case of a vacuum. If we're in a vacuum, we can't have any charge, and we certainly can't have any moving charges. So two terms in our Maxwell equations are going to go away. We're going to lose this term. Gauss's law is going to become, the integral of E dot dA is going to become 0. And Ampere's law, we're going to lose our regular current term, and we're just going to keep our displacement current term. These equations on the right, don't worry about them. Those are known as the differential forms of Maxwell's equations, but they're important in that I can apply mathematical operations on those to get to these equations. The math is a little bit not tricky, but involved. So I'm happy to go through with anyone if you want, but it's beyond the scope of Phys 2. But what's cool is for both the electric field equation, or both electric fields and magnetic fields, if I do some mathematical manipulation on these Maxwell equations for Maxwell equations in a vacuum, I'm going to get the same form as the wave equation. And this is basically just what Maxwell got. He basically theorized that light is going to be a wave. It has to travel as a wave because it satisfies the wave equation. And he predicted the speed of light because just following with the form of the wave equation, if I have 1 over the velocity squared here, then it follows that the speed at which light travels at is 1 over the square root of epsilon naught mu naught, which I think is pretty cool. No chat questions. Cool. All right, so monochromatic waves. This is basically just telling us that when we consider these waves right here, or this wave form, usually we consider it in the context of an electric field or a magnetic field. So for instance, we'll say the electric field is equal to some amplitude, let's say E max, times cosine of omega t minus kx. That's basically all I'm saying, is that for a certain frequency, each frequency corresponds to a different color, and that's why these waves are sometimes called monochromatic light waves. And electromagnetic waves are also transverse, meaning that the electric and magnetic fields are perpendicular to the direction of propagation. And I think that's pretty nicely visualized in this picture. So this wave, for instance, would be propagating along the z-axis with speed c. The electric fields would just be moving up, sort of parallel to the x-axis. The magnetic fields would be perpendicular to that along the y-axis, but of course with a different amplitude. That would be the magnitude of the B field vector, and that's just the magnitude of the E field vector. Cool. And I think that concludes my section. I don't know if Tyler's still there.
Sounds good, Nick. Yeah, I'm here.
Cool,
You
cool.
have one question in the chat.
I do. Let's see. Should it be sine for electric field? You mean right here? Where I wrote that example equation out. Yeah, so it definitely can be either sine or cosine. And really it doesn't matter because sine and cosines are the same exact thing, except for one's displaced by a factor of pi over 2, sorry, I think. Yeah. So really it doesn't matter too much whether we use sine or cosine. It's going to be the same wave either all. Not either all, overall. So you can use sine or cosine in whatever problem they give you, or unless they tell you the electric field at a certain point is given by this cosine function. Basically, the distinction there doesn't matter too terribly much. Hopefully that answered the question.
Awesome. Sounds good. Thank you, Nick. I will start sharing here. Hopefully this works okay. All righty. That should be okay. Cool. All right. You can see that, right, Nick? I would assume I can.
Yeah, I can see it.
Cool. Awesome. Well, thank you so much. So awesome. So yeah, guys. So just to recap of where we are, Nick went through topics 4A and 4B. I would deal with displacement current, Maxwell's equation, things like that, and the relationship, I guess, between voltage and intensity and all that good stuff. Let's see, we have a question here real quick. Will there be additional practice exam questions online Kappa, or should we just review previous ones from Mailbox? Yes, so great question, Ava. Actually, if you go into the block 4 section, there is 2 tabs down at the bottom that says sample like final exam questions from 2011, and then one was from 2017. So please absolutely go through those 2 folders. They're fundamentally no different than the folders you've seen before in previous exams, except with optics problems added in there, right? Otherwise, they're the exact same. But I would recommend starting with the final exam problems first, and then going through actually your previous exams to figure out, places you've kind of gone wrong, questions you want to brush up on, things like that, right? But does that answer that question for you? Awesome. All right, great question. Awesome. So yeah, just want to reiterate one more time. If you do have questions, please feel free to unmute yourself or just say something in the chat. Nick and I'll be more than happy to answer those for you. All right. So so like I said, just recap where we are. Nick covered 4A and 4B. There's 2 topics left in optics. One is on geometric optics and the other is physical optics. So I actually don't have too much to talk about here. Geometric optics, I'm sure you guys have noticed, is actually not too mathematically involved, really. It was really just lots of triangles and just angles and stuff that we've used back in geometry. So hopefully this makes quite a bit of sense. So let's do it. So yeah, the first really major topic we learned about in geometric optics is the idea of a reflection, right? So keep in mind, reflection and refraction are 2 different things, right? Reflection really just means, obviously like looking in a mirror, you're seeing your reflection, right? Reflection just means any light waves that come in on some surface reflect off of that same surface at the same angle. Right, so keep in mind, there are some questions that will ask you for reflection versus refraction, right? 2 very, very different things, right? So keep in mind, you read what the question is actually asking for, because if it's reflection, you don't actually have to do any work at all, right? Refraction means you have to do Snell's law, and we'll get to that in a minute. But just a quick recap, reflection just means light coming into a surface bounces off or reflects off that surface at the exact same angle, right? So just keep in mind, you have no work to do there, right? If it's reflection. Okay, but that doesn't happen too often because we want you guys to show us what you know. So reflection doesn't happen too often. What we see more often than not is the idea of refraction, right? Refraction by definition just means bending, right? A bending of a light wave in this case, right? So this happens whenever a light wave enters, some prism or something that we give you, or water, things like that, right? Light waves actually bend according to Snell's law right here. Right? It says that the index of refraction of your first surface multiplied by the angle of incidence of your first surface, right? That term right there is equal to, well, the same thing on the other side, except that deals with the entire other surface, right? So keep in mind, we normally have one light wave leaving something and joining something else, or vice versa, right? Just most of the complications from these problems come into play when you're trying to figure out which angle goes where, for example, right? And anytime it says air, for example, right, your index of refraction is 1. All that good stuff. But what is index of refraction? Well, index of refraction is a number that's going to be greater than 1, and it really just describes really how fast in relation to the speed of light that a light wave moves through your medium, right? So the equation to calculate that, right, you might need it on your exam, is this sucker right here, right? It says that n, your index of refraction, is going to be equal to the speed of light in a vacuum, so 3 times 10 to the 8th, divided by the divided by the velocity of that light wave in your medium, right? So it could be water, it could be, I believe you guys had a homework problem on like argon or some weird thing, right? It'll give you the velocity of that light wave whenever it enters a new medium, and then you just divide the speed of light by that to get your index of refraction. Keep in mind that the index of refraction is always going to be greater than 1 for problems we do here on Earth anyway, because out in space, the index of refraction is exactly 1, right? So everything we have here on Earth, that number is going to be greater than 1. Right, so anytime you do that and you get a number less than 1, then you might have messed something up, right? So just keep that in mind. Index of refraction should always be greater than 1. All right, any questions about Snell's law? And like I said, we can do some examples on optics and whatnot because that's the newest unit. But I feel like Snell's law is pretty well understood by most of you guys. It's just like I said, comes into play, and you have to figure out if it gives you one angle, exactly where does it go? Right, so I find it helps to either make a table for yourself or figure out, okay, what is leaving, what wave is leaving, what wave is entering, that sort of thing. Any sort of system you can give yourself, figure out which one goes, which angle goes where, that sort of thing. All right, but like I said, we can go over some of those problems, so no big deal there. And then one last thing as far as geometric optics is concerned is the idea of total internal reflection. Right, so the best physical example I can give you of this phenomenon is think about a diamond on a ring. Right, the reason why people charge you so much for a diamond or a higher quality cut diamond is because they prioritize total internal reflection. Right, so the more expensive a diamond is, the more light waves will get trapped inside of that rock. Right, that's why it's more expensive. That's why it sparkles more. Right, so really just a quick little physical world example of how this might apply. But if you think about it in terms of diamonds or shiny, whatever, I feel like it applies much, Nick. It applies much easier. So what this means is that when a light wave tries to leave some material, right? Same thing about like water or like I said, or like a diamond, right? When it tries to leave that material, right? It comes in at exactly the right angle such that you get this sort of parallel path with the edge or the boundary of your new material, right? So your light wave actually doesn't escape the first material, right? It just follows along that boundary and stays inside of your first material, right? So hence total internal reflection, right? Like I said, main idea is it does not escape that medium, right? It will always stay in there as long as it is at what is known as the critical angle, right? So that critical angle, right? I read it normally as theta c right here, right? Is going to be, you can solve for it in Snell's law, right? Because you know that the other side of Snell's law has to be equal to sine of 90 times whatever that index of refraction is. More often than not, it's going to be air, right? So N2 will more than likely just be 1, right? But it might tell you going from one diamond to another, something like that, right? But what's important is that sine of theta term goes to 1, right? Because your light wave is it is refracted along this path here, right? So now you can't really see that because it's in red, but it is along the path of that boundary, right? So your angle is always 90 degrees between the normal right there and the path, right? So that's the most important thing, is realizing that sine of 90 right there can be canceled out just to be equal to 1, right? Like I said, N2 could be anything, could be air, could be whatever, right? What's important is that index of refraction has to be lower than the one you are leaving, right? That is what this paragraph down here is saying, right? You have to be escaping or trying to escape a higher index of refraction than you are going into. Right? It doesn't make much sense for light to get trapped in air, so to speak. Like that just doesn't make much sense to us, right? Whereas if you talk about light getting trapped in a diamond or in some sort of prism or something like that, then that makes a little more sense, right? But keep in mind that index of refraction, if you're talking about N1 going to N2, right? N2 should be less than N1. Okay. See a question real quick? Yeah. Yeah. So Lisa, that's a great summary. So TIR can only occur when it goes from high to low index. Exactly. Right. You're going from a high index of refraction to a lower index of refraction. Think about it getting trapped there, so to speak, right? So one you're trying to leave is greater than the one you're trying to go into, right? But that paragraph right there that I've highlighted is a great summary of that. Right, so TIR is probably, I guess, the most confusing part of Snell's law, and I guess where geometric optics comes into play. So, are there any more questions about this topic? Right, solving for theta crit, anything like that? Like I say, we can go through a problem. It's not a big deal, but just questions off the top of our heads. Okay, looks like there is no questions there, so I will move on then. All right, so the last topic we talked about in block 4 was the idea of physical optics. So really, when you think of physical optics, think of like the double slit experiment, right? Think of shining a laser pointer through a hole in a wall, something like that, right? That's what we mean by physical optics, right? And so the idea is that light can be both a particle and a wave. And if you're interested in more about that, it's quite the YouTube rabbit hole, but it is pretty cool to learn about. So, but as far as this class is concerned, right, really that boils down to two major things, right? The idea of constructive interference, right, and the idea of destructive interference, right? So the best way we can use to really explain to you guys what the difference between these two is, but think about the fact that if I had two light waves, right? In the constructive case, I have two waves that are what we know as in phase, right? So that means that they are peaks at the same points and valleys at the same points, right? So that means if I were to look at, let's say, I'll mark it in purple, this spot right here, I would get constructive interference if these two waves are added together, because I have a peak here and a peak here to be added together. So really the reality is I would get a rather large peak here, right? And a large valley, large peak, large valley, so on and so forth. All right, constructive interference means they are adding together, okay? And how we represent that in as far as mathematics are concerned, right, is this equation right here. Let me highlight it in orange, keep constant colors here, right? It says that the path length difference, delta R, right, is an integer multiple of the wavelength of the light, right? So where integer multiple comes into play right there, that is M, is our wave number, right? And for constructive interference, it will always be some whole number integer, right? So 1, 2, so on and so forth, right? So always be some whole number integer for constructive interference. Right, and then on the other end of the spectrum, destructive interference, you have your path length difference. It occurs when it is a half integer multiple of the wavelength, right? So where M is still, I guess you could think about it this way. I guess M is still a whole number, but it gets added with this half term here, right? So you will always have a half integer on the right-hand side of the destructive equation, right? So you can think about it whichever way you want, right? But M is a whole number for constructive, and then this quantity will be a half integer for destructive interference, right? And if I were to draw just a quick picture of what that looks like, I don't have my two waves here, but they would be what would be known as out of phase, right? So really I've got a peak where I've got a valley and so on and so forth. Sorry, those are terrible drawings, but if I were to add up these two waves at this point, right, notice how I would get a resulting wave that would look something like that, right? It would just cancel itself out, okay? That's what we mean by destructive versus constructive interference, right? And then I see we have a question here. Sorry, it's not a dumb question, believe me. How do we know what to use for M? So yeah, so let me go clarify that again. Because we've got these two forms of the equations right here, M is always going to be a whole number if you remember the difference between destructive and constructive, right? So M is always a whole number. You always plug in 1, 2, or whatever for M, right? It's just that in the destructive case, you'll get half, and then constructive, you'll just get that whole number, right? But I think I know what you're trying to say, Melissa, in the sense of like in as far as long capital problems are concerned, it will usually tell you straight up, hey, M is this, or it will say something like at the first instance of constructive interference, something along those lines, right? So it's usually not explicitly given to you, right? But there's key context clues in there that says like, yeah, first, or like the first occurrence of destructive interference or the first occurrence of constructive interference, right? And whenever it says that, obviously that corresponds to the number 1, right? Does that make sense, Melissa? Does that sort of answer your question? I wish I had a little bit more of a definitive answer, but we are kind of finicky when it comes to that. So awesome. Good. Glad that answers your question there. Very good question. Does anybody else have any questions when it comes to physical optics? Like I said, this is really the only two equations that apply to slits per se, but we got a little bit more to talk about. So looks like we're good to go. All right, cool. We're free to ask any more questions. So, there we go. Will there be a question on an exam where 2 answer choices are based on the number for M? No, never. And that is something in this class, we never really ask you for M. It's not really like it's usually not something that it's like of particular value to us necessarily. We're more concerned with with the things like the path length difference itself, right? So that quantity right there, or even sometimes the wavelength, things like that, right? M is usually far and away not something we would ask you for. In fact, I've never seen a problem ask you for that, right? So you should be okay, but just in case you know what M is your path length difference, right? It describes at one point along my wave that I'm at, basically. So just one more pictorial reference for you. For example, this point right here, get rid of that. This point right here would be the first instance of constructive interference. So M would be 1, right? Versus way down here, I've got the third instance of constructive interference. So I'd say M is equal to 3 there, right? So like I said, just to give you a little more background as to what that is actually referring to. But no, I really would be, I don't think we would ask you anything like that. Does that answer your question? Cool. Thank you. Appreciate it. All right. And there we go. Got another question. Awesome. Would the R difference change to reflect that? Oh, yes, absolutely. Very good question. If you're talking, it depends on if you're talking about double slit experiment versus when you're talking about just like 2 waves, one behind the other. And Nick, correct me if I'm wrong, but in the double slit experiment, if I were just to draw what that would actually look like up here, and then I got my wall back here, right? You'd have a couple different equations for the double slit experiment, but really, if I was talking about this interference pattern that would be on the wall over here, so something like this, and massive something in the middle, something like that. And I think what you're referring to is if I was talking about this point right here versus this point right here, right? Your path length to the center would be a little different, right? That would be, for example, I'll call that Y1, right? And that would be Y2 there. Right, so if we're talking about the double slit by itself, then yeah, you have this equation for it, dy over r equal to m lambda for constructive interference, where that y difference, that is what I'm talking about there. Right, but if you're just talking about like one wave behind the other, so to speak, so like the 2 antennas homework question you guys had, you were talking about one antenna being here, one being here, and you were moving from here over to the left. Right, here is where you would have sort of like a more traditional path length difference, where you have this one was R2 and that one was R1, and you'd have pretty consistently the same distance between each one. Does that make sense? That's a very good question. I honestly was not expecting a question about path length difference, but it's a good question. Does that make sense? Cool, awesome, good job, guys. Very good questions. All righty, so like I was saying, the next really the last major topic in optics, as far as physical optics goes, is the idea of Bragg diffraction, right? And it's not super important who this guy Bragg was. He did some really cool experiments within the X-ray domain, but really all you guys got out of it was this fancy equation here, right? And this is based on 2 different light waves having 2 different incident angles, right? So think about one light ray coming in, I guess something like that, right? Where that would be theta 1 versus some light wave coming in like that, right? Where that would be theta 2, right? That is what this original equation is based on, right? If you have 2 different incident angles, that's what that's based on, right? But, excuse me, the simplification that Bragg made, right, is if you have the exact same incidence angle, right? So really you have this right here, and I've got basically 2 light waves coming in at exactly the same angle, theta 1, well, then I can just simplify it down to that nice, easy form right there. Right, and then as Nick mentioned down here, it's really nothing more than a constructive interference condition, right? Just adding the 2 together, and especially because we have on the right-hand side here, this m lambda term, not m plus 1/2 lambda, right? That tells you that it is constructive interference. Right, so yeah, that problem, or when it comes to Bragg diffraction problems, they either tell you straight up it's like, hey, these are X-rays or something like that, or I know there's a problem that says Bragg diffraction uncertainty, right? So in that case, you would just use this equation right here, right? But there's not too much difference there. All right, that's a good question. What does D represent? Well, in the traditional form of the Bragg diffraction experiment, right, he had basically a prism that kind of looked something like that, right, the corner of it, and he had a separation distance between that prism, right, the 2 faces of that prism, right? Or more formally in your guys' studio, you had a lattice structure, right? We have 2 rows of atoms or molecules, right, separated by some distance d, right? So to summarize, I guess how I would answer that question, it's really just the spacing between two sets of atoms or two surfaces, right? The two surfaces that your light waves are coming into contact with. Does that answer your question? It's also a very good question. Okay, I'll take that as yes. Cool, awesome. Very good question. Yeah. So, and then something I will reiterate for that distance d, it's either given to you in a picture or it will literally say d is this. Right. So yeah, that's pretty straightforward. How is theta measured for this? Also a good question. And that will be, as soon as the moron going down my street stops being so loud, that will either be given to you straight up or it'll be shown on some diagram. Right, if you're talking about your studio question in particular, that one looked a little bit like, I think a little bit like this, right? If you excuse my terrible drawing, it looked something like that maybe, where it gave you that theta between the light wave and the normal, right? As far as the traditional Bragg diffraction thing goes, it won't give you that, right? It'll have some picture, looks like that, right? It'll say what that theta is, right? But also a very good question. Does that answer your question? Yes, measured from the normal, exactly, yes. Every angle we ever deal with in geometric optics, really in optics in general, is measured from the surface normal, right? So yeah, that's a great summary is what how I would summarize that. Cool. All right, and then we have a slide about the fitness car and pacer test. You remember that from high school? Good times. All right, as far as my material is concerned, that is all I have. You guys have answered that poll, and overwhelmingly, besides optics problems, people wanted to see electrostatics problems, which comes as no surprise to Nick and I because it's been 3 months. So what's going to happen is I will go over some optics problems. Nick, I'm thinking we do probably two each, and we'll see where we're at with time, and we can go back and do some more. That is okay with you, and then just go from there. That sound all right?
Well, looking at the split, just so it's more like even, if you want to take electrostatics, I'm happy to do that, and I'll take like optics and magnetism.
No, that's totally fine. I honestly don't mind at all.
I'm happy to do whatever.
No, you're good. Okay. I'll start with a few optics problems, then I'll pass it up to you for electrostatics, and then we can go from there. Okay.
As for the question in the chat, are teachers having off hours tomorrow? I don't think so because it's rest day or dead day or whatever they changed.
Yeah, I'll second that. I'm honestly not 100% sure. It's a good question. But yeah, there have been multiple announcements and whatnot, and I'm sure you could reach out to one of them just to ask, right? Yeah. But if you guys, I will say, if you guys do have any questions that you can't figure out, or your friends don't know, whatever, feel free to email. Either one of us will be more than happy to answer you, as long as it's not like 3 a.m. That's not a problem by any means. So feel free to reach out. But other than that, like I said, that concludes our scripted session necessarily. So I will go over to Long Kappa here and pull over a couple of optics problems. I'm going to my general notes thing here. All right, and then we can pass it off to Nick for some electrostatic stuff. So I know I didn't give you guys the choice of what problems you necessarily wanted to see, but the good news is there's really 2 or 3 categories of problems that we can even ask you about as far as optics are concerned. So I'll kind of write them out here, and we can maybe get some answers in the chat what we want to see. So the first one I remember most is obviously Snell's law problems. Snell's law. All right, so really finding incidence angle, finding refracted angle, things like that, right? That's really what I would say the first major topic is, or not really the first, but one of the major topics. Second major topic I can think of is what I would call antenna problems, right? So really you're given some power or some intensity or something like that, and you're asked to find the voltage in the antenna, some form of that. So I'll say antenna problems there. And those problems really bring in more and more of topics 1 and 2, and I guess a little bit of 3 as well, right? And then from there we could say, yeah, physical optics type problems. So physical optics, so double slit, things like that. All right, and then how could I forget about displacement current? All right, but I don't see too many multiple choice displacement current problems, right? In fact, I don't think I found any at all in your guys' review set.
I think literally the only displacement current problem we ever have is the one homework problem.
Yeah, exactly.
Yeah.
Thank you. In fact, I will just give myself the liberty of just crossing that one out, right? So just to put everything out there on the table, just to describe what we all have. But so really it's between these 3 problems, as long as I'm not forgetting something, which I think we're okay. So I guess as far as some answers in the chat, what would people like to see most? We can the problems are pretty quick and easy. So honestly, we could probably do all three of them, right? But if you guys were to say which one of these is giving you guys the most trouble, I think I can guess which one it might be. But if we get a couple answers just to know where to start, that'd be awesome. Okay. Yeah, that's exactly what I thought. Yeah, physical optics and slash antenna problems. So I think it's fair to say that, yeah, ones would be on the exam. If we knew, we would definitely be doing those. But yeah, so it looks like overwhelmingly physical optics problems. That sounds good. I will start with one of those problems. I believe I found one of them. Check it out. I don't remember exactly what it's called off the top of my head. I think the only physical optics problem, well, there's technically two. So if you go to the 2011 set in Long Kappa, so like I said, block 4, the 2011 final exam review set, there's a problem called interference spacing. And then a problem before that called Bragg diffraction uncertainty, which we can go over real quick too. It's not going to take any time at all. But I'll start with interference spacing. Right. So if you go to that folder, it's about halfway down, and it should load for me just a second. It should say something about 2 AM radio towers. All right, so I'll give you guys a couple of seconds to get there, right? But I will write out what we're actually dealing with here. So it's called, 2011 set. It's called interference spacing. Interference spacing. Cool. All righty, and for those of you that may or may not have it pulled up, I will just read it to you real quick. So it says, consider 2 AM radio towers operating at some frequency. Obviously, Long Kappa generates different numbers. The towers are separated by some distance. So in between the two towers, there'll be several places where the two signals interfere destructively. What will the separation between those places? What will be the separation between those two places? It would probably be a good idea to make a sketchy situation. Yep, very good idea. So I will, first of all, write out what I know. I'll write out that the frequency, right, is some number. Right, for me, I'll just say it's 1,000, so we can all be on the same page. All right, and then I'll have some distance d, I'll call it, whereas the tower separation distance for me is about 7,000 meters, right, or 7 kilometers. All right, I would get in the habit of writing out everything in terms of the units you're going to use. So this would be 100,000 or 1,000 times 100. I'm not going to write that up. 1,000 kilohertz, but 1,000 times 10 to the 3rd hertz, right? So we are trying to find the separation distance between the two places of destructive interference. All right, so first thing I'm going to do is take its advice and draw a quick picture here. All right, so I've got one tower there, and I'll put one tower in red over here. All right, separated along the ground by some distance, d, or 7,000 meters. All right. And they are broadcasting at some frequency, right? The frequency is the same for both of them, so that's not something we have to worry about, right? But we are concerned with, like I said, the distance between destructive interference patterns, right? So first thing we have to do really is figure out what equation, belongs to destructive interference, right? So I did cover just a few minutes ago, right? But remember, for destructive interference, right, is going to be that half multiplier, or that half integer multiplier for m, right? So we'll go delta r, or r2 minus r1, right, is equal to m plus 1/2 times lambda. Right, where again, m is that wave number, right? But destructive takes into account for us. So we just plug in a whole number for m and we will get a half integer on this side of the equation. Right. So just to simplify that for you, I know that can be a little confusing, but if you just remember, destructive has to be multiples of half and constructive has to be multiples of, well, 1, right? 1 integer, then you'll be good to go. All right. So like I said, we are asked for the separation between successive destructive places. Right. So really what we're asked for is really just the left-hand side of the equation. Right. Separation distance, anytime it says distance, the left-hand side of your constructive or destructive interference equations are going to be what you're looking for, because this deals with actual distances, actual meter distances. Okay, so good news for us is this problem is pretty straightforward actually. Once you realize what destructive interference actually is, right? It's like I said, it's those places where those waves, right, are out of sync with one another, right, such that we will get a net wave of 0. I did not draw that correctly. It's my bad. Right, so that is valley, peak, valley, peak, valley, peak. Yeah. Right. So when we add the two together, right, in blue, we will get a net 0 wave there. That's our goal. Right. And from here, right, the easiest thing for us to plug in to find out what the distance between successive places would be is really just to start where m is equal to 0. Right. So we get 1/2. Right. And then I could plug in 1 just to see the difference between those two places. But at that point, I know that the distance between 1/2 and 0 is going to be the same as the distance between 1 and 1/2 and then 1/2, right? Because they're all separated, or sorry, I guess, yeah, 1.5. Yeah, exactly. Because they're all separated by that same distance, right? They're perfectly out of sync with one another and they never change that. Right. So really just to simplify our process here, I'm just going to plug in m equals 0, right? Because it would be the same if I plugged in anything else. Right. So I have delta r here. Right, what I'm looking for is equal to 1/2 lambda. Right, and you guys being the bright students that you are, realize at this point we don't have a lambda. We don't have a wavelength of light. Right, but good news is a little bit higher on your equation sheet. I believe like 2 or 3 rows up, you have an equation for lambda. Right, that says, I will say over here, right, lambda is equal to c, the speed of light, divided by the frequency of your wave. Right. So really, I can just plug that sucker in right there, C over F, right? And I can solve for my path length difference, right? It'll be some number, right? Obviously, I have different numbers than you guys, but that's really all there is to it, right? So all of that amount of words just to say, hey, find out what delta R is, right? By plugging in 0, right? So I feel like that one is fairly straightforward, and this is the sort of thing you guys can come to expect as far as these problems are concerned. Right, it'll either be constructive or destructive, and it'll say either some distance between two successive places, or like I said, maybe it might ask for wavelength at some point in time, or the frequency, maybe, right? But at the end, again, at that point, you just know that that equation holds true, right? So not too much really going on there. All right, are there any questions about that problem in particular? Cool, take that as a no. All righty, and then I will do one more, and then Nick, I'll pass it off to you for a hefty block 1 stuff.
Sounds
and
good.
the one I am going to go over is from the 2017 set. It is called straight antenna. All right, this is what I would say is probably one of the more difficult optics questions that you might be faced with, but I have seen it quite a bit, right? So it would not surprise me if this one came up. And so again, on the 2017 set, right, it'll be a problem called straight antenna. I'll write it out right here. 2017 set, straight antenna. Cool. All right. So we are talking about watching the Avalanche's playoff game against the Detroit Red Wings on cable. I have no idea when that question was made because I have not seen the playoffs. All right. So knowing that the game is also being shown on a local station, you straighten out a metal coat hanger to devise an antenna for your TV to try to pick up the rest of the game. The local TV station is broadcasting signals into a sphere at some power is equal to, I have 175 kilowatts for that, right? But keep in mind, it'll just be some number. If our straight antenna has a length, L equals 0.25 meters, right? And your TV is at a distance 36 kilometers away, 36,000 meters away from the broadcast tower. What is the maximum possible signal voltage produced by your makeshift antenna? Express your answer in millivolts. Right, so all that to say, we are looking for a voltage, right, or an EMF if you prefer, right? Either way, that's an awful E. Right, so that's what we're looking for. We're looking for a voltage, right? And so immediately off the top of your head, you should be thinking, hopefully you're thinking one of two things, right? You're thinking either Faraday's law, or you're thinking the voltage expression that we learned way back in Unit 1, right? That integral expression, right? And then upon further thought, hopefully realize that in this problem, I have no mention of magnetic flux anywhere, right? Nothing at all. I have no like quote unquote loop necessarily. I mean, I have a straight antenna, but I don't have a loop to work with. So really, your only option is to work with this integral that we learned, like I said, back in Unit 1, right? The negative integral of E dotted with dl. Right, again, because there is no mention of magnetic flux or anything that would help me get there, period. Right, so then again, is just taking stock of what you got in your equation sheet and what we've learned about voltages in the past. All right, so let me just check and make sure there's no questions about that quite yet. distance doesn't matter. Yeah, sorry, it was just, yeah, just a second. Aiden, that was about this problem, right? Or was that about the last problem? That's my bad, I didn't see it. I think that was about the first problem. Yeah, okay, cool, just check it, yeah. And just to answer your question, yeah, distance actually didn't end up mattering. Just wanted to toss it out there, but good question. All right, so back to the straight antenna here. Yeah, so did that, please, like I said, please unmute yourself and ask if you had any questions about that thought process I just went through. Right, we are asked for a voltage, right? And I know in class there's only really a couple of avenues I could take, right? Most predominantly it could be that voltage integral or Faraday's law, right? And Faraday's law, like I said, doesn't make sense, right? Based on the amount of information we're given, right? And the amount of work it would take to get that information, right? So I feel like it might be pretty helpful, right? Just to, like I said, take a mental note of what you've got and where you're trying to go, right? But like I said, this is where we are trying to go, right? We're trying to, basically we're going to integrate along the length of that antenna to find out how much voltage I've got in between the two ends. Right, that's going to be my goal, right? I'm going to integrate the electric field over some length of antenna. Okay, so with that goal in mind, right, I'm going to take a bunch of steps in order to get to my electric field, right? And so the electric field is probably the biggest quote unquote hoop to jump through as far as the optics unit is concerned, just because we haven't dealt with electric fields in a long, long time. But if you were to look on your equation sheet in the optics section, which I know you would be at this point in the exam, like what the hell do I do with electric field, right? You would see an equation for intensity, right? I usually write it as I, but it might be given as S on the equation sheet. It looks like this. It says 1/2 C epsilon naught times the electric field squared, right? And that is in your optics section, right? But I know most of you would probably have found that, right? Because you're just trying to match letters, right? You're looking for that right there, right? Which is good because it does translate directly over, right? So what this tells me, right, is the intensity of some light, right, or some light wave is equal to 1/2 times c, the speed of light, times epsilon naught, the permittivity of free space, which we've dealt with before, times E, the electric field squared. Okay, so this is pretty good, right? I know everything in this equation except for E, right, which is what I'm looking for. Right, so that's fantastic, right? We just have one small problem in that we don't know what I or S, the intensity of the light is, right? But then again, you might look up a little bit further on your equation sheet and realize we do have an equation for that as well, right? I, like I said, or S, whichever way you prefer it, right? We have too many I's, so, or we have, yeah, too many I's. If you prefer to write it as S, that's no big deal. But you should see something that looks like this. It should say P over A, right? And I normally write it as POW, just to remember as power. All right, power over area is the intensity of a wave, right? So now this is fantastic, right? I could go back to my given information in the problem, right? I've got power right there, right? The problem statement says it goes in a spherical fashion, right? So I know my area, right? And this is great. I can find intensity, and I can go find electric field, right? And then I can go find voltage, right? So what I've just defined for myself is a very clear path as to what I'm supposed to do in this problem, right? Because, like I said, it's kind of difficult to translate electric fields to voltages sometimes, and even more so when it's talking about like waves in general, right? So that thought process will do you pretty good on the exam if you're just confused to all hell as to what to do, right? But with that being said, I will start at the last thing I wrote down here, right, which is that intensity equation, right? So this one right here, okay? So I'll write out my solution here in blue, right? So I'll just keep using S because I believe that's what's on your equation sheet. So power over area, right? In my equation, I am given power, right? So I'll just write that as 175 kilowatts, I believe, right? And the area, right? Remember, it says that light wave, or that wave, I should stop saying light wave because it's not a light wave, but it is a wave that is moving out in a spherical fashion, right? We say that from any antenna or something like that, right, the associated waves move out in a spherical three-dimensional fashion, right? So that's what it means when it says sphere, right? And then hopefully by now you guys remember that the area of a sphere is 4 pi r squared, right? It's not pi r squared, right? I know it looks like a circle, but it's a sphere, right? The area of a sphere is 4 pi r squared, right? So don't forget about that 4, right? And that r, right, describes the radius between whatever is generating my wave to the point at which is experiencing that wave, right? And if you would go back to look up at the problem, you realize, well, we really only have one distance, right? Stop erasing. We only have one distance, so I should probably just change that to be r, right? Just so it's consistent, right? So after plugging in what that radius and what that area would be, right, I would get some number for intensity, right? I'll call it S naught for a variable. Okay, so at this point, this is great, right? I've got step one, right? Totally done. I got my intensity, so now I actually erase something. Right now I can go on to step two here, right? I can try to solve for my electric field. Right, so let's rearrange that equation for E field. Right, so E is going to be, excuse me, the square root of 2s over c times epsilon naught. Yeah, just making sure I did my algebra right. Yep. So that was just rearranging that equation to solve for electric field. Right, it could look a little better. Right, and notice here I've got all these numbers now. Right, intensity was my problem before, but I do have it now, so I'll just type in E, or for S naught there, I'll just type in S naught instead of S. All right, and that would give me my electric field. Right, that would give me some number for my electric field. Okay, so now this is great. Right, I'm done with step two. Right, so let me erase some of these arrows here. Right, put a check mark next to that step, because I am done with electric field. Right, now the last step I have to do is actually plug that into my integral and solve for what the voltage would be, right, by integrating along the length of my antenna. Right, so I will take that equation down here, right, E dotted with dl, right, is equal to voltage. Right, and then I just wanted to, oh, sorry, I see a question here. Give me 1 second. How would you do it for a circular loop antenna? That is a great question, and if we have time at the end of the block ones and things like that, types of questions, I completely know the question you're talking about. It was a studio question. So as far as the brief answer to that, you would have to, the question you're talking about in studio, it asks for the radius of that antenna such that the voltages were the same. So you would go through this entire problem to find the voltage, and then you'd work your way back using Faraday's law that time in order to solve for what that radius of that loop would be, right? But that is a great question. Would the R in the area be the given value for I or L or D? Gotcha. That is a good question. The R in the area was the given value for distance D, like the distance between your antenna and the places in which you're experiencing it. L right up here, right? That is the length of your antenna, right? That's the length of your antenna just as a thing, right? Does that make sense, Ashley? Cool. Good question. Yeah, and Robert, like I said, great question. After we finish block one / block three stuff, if we have time, when I don't mind staying after to talk about it as well, we can go through that question you're talking about. Because for a circular loop antenna, the process is a little different, except because you have to bring in Faraday's law, right? But since the straight antenna problem is on the review set, that's the one we decided to go over. Right, so good question. Hold your horses. We can talk about that in a little while if you want. So where was I? So on the voltage equation down here, right, just a quick little recap of some things we may have forgotten. Right, remember that this negative sign, right, usually refers to the fact that the bounds on this integral are usually flipped. Right, so remember from calculus, right, you can keep the negative sign there and have bounds that look something like this, right, L to 0. Right, some positive distance to some smaller distance, right? But calculus, like I said, doesn't like that, right? So it slaps the negative sign on there instead, right? But for all intents and purposes, right, you can get rid of that negative sign and flip the bounds, right? That's the rule we used back in Calc 2 in order to solve for what the area under a curve would be. Right, so both those are equal to each other. And anytime it asks for voltage in an antenna or things like that, it's always going to be a positive number, right? I would never say that my battery has minus 10 volts, right? You wouldn't power some, remote or something like that with minus 10 volts, right? It just doesn't make any sense, right? So voltage, like I said, is always when you're talking about some real world example, is always going to be some positive number, right? So from this point forward, I'm going to ignore that negative sign and flip the bounds, right? Just like I did right there, and plug in that electric field expression, right? And multiply it by DL. Right? And if you're wondering where those vector notations in the dot product went, well, you can just reason it out, right? The electric field, right? If I've got some antenna, right? I distinctly remember Nick going over this in block 3, right? Remember you have some separation of charges, right? Positive and negative, and your electric field flows like that, right? Well, the differential length vector has to be along the length of our antenna, right? So notice how those two are perpendicular to each other. Right, and the E field will always be constant inside this antenna. Right, so really what I have here is just E times DL. Right, but yes. So get rid of the dot product, get rid of vectors, all that good stuff. Right, and notice in this electric field, right? This expression right here, none of that changes as I move along my antenna, right? So I could just pull it out of my integral, right? 0 to L of integral dl, right? And the integral of dl is just going to be L, right? So the answer to this problem is just going to be E times L, right? Where E field is that expression right up here, right there. Right, so I would just plug that in down there and I would find out what my voltage would be. Keep in mind that you want your answer in millivolts, right? And on your exam, they might try to trick you with some units there. So keep in mind it wants it in millivolts, which is 10 to the minus 3 volts. Okay, so that is enough of that question. I believe that's, like I said, one of the more complicated ones you might see just because it's a multiple choice question. But other than that, that is all I've got for you as far as optics are concerned. As far as the things I've seen in the past before necessarily. But if you have more questions, like I said, feel free to reach out or ask any questions later after most people have gone, that sort of thing. Totally fine by us. But other than that, if there are no questions about this problem in particular, I will pass it off to Nick for electrostatics, block 1.
Thank you. Sounds good. Excuse me. So there's really 3 problems or 3 categories of problems from electrostatics. I feel like there's Coulomb's law, Gauss's law, and voltage problems. Does anyone have any preferences for those? I'll probably just do 2 and then we can recalibrate to see how we're doing. Gauss's law, voltage. So Coulomb's, I'll put them in the, I'll share my screen and I'll write them out like Tyler did. We had a Gauss's law option, a voltage problem option, and a Coulomb's law problem. And let's see what the chat says. So Coulomb's, Gauss. Gauss and Coulomb's. Okay, yeah, that's what I was thinking. Gauss's and Coulomb's law are usually the trickier ones there. So let me find a problem for Coulomb's law first. And I'm gonna pull from, if I share my screen. Cool, hopefully you guys can see that. Well, I guess that wasn't too bad. I'm gonna pull from the sample final exam questions fall 2017. And the problem is called quarter circle. So it says we have a quarter circle of charge with radius r arranged as shown in the picture. The segment is uniformly charged with a charge density of lambda. And the problem is asking us what are the horizontal components of the electric field produced by the shape as seen at the origin, and what is the vertical component of the electric field produced by the shape as seen at the origin. So basically, if I just start out by drawing a picture, or I have a picture drawn, but basically we have charge along this line. We have charge uniformly distributed along this quarter circle. And positive charge is gonna make electric field lines go away from it. So we have maybe electric field lines going like that and away from it in the other direction. Something like that. Maybe it's a little bit hard to predict because it's not like a line or something, but basically it's asking us to use Coulomb's law to more precisely figure out what are the vertical and horizontal components of the electric field at the origin. And really, even before doing any math, by virtue of the fact that the quarter circle is uniformly charged, I have an equal amount of charge above the x-axis as I do below the x-axis. So if I clear my lines, so all the charge that's coming from this top here probably won't cancel out in the x direction. I'm probably going to get some x component of my electric field. But right off the bat, I can see that since I have an equal amount above the x-axis as I do below the x-axis, I'm probably not going to have a vertical component of my electric field. That'd be different if my charge density wasn't uniform. If my charge density, for instance, if I had more charges here at the bottom of the quarter circle, then these electric field lines would be stronger and more powerful than the ones coming from the top. And I would have a net vertical component to my electric field, but it's uniformly charged, so that's not the case. So basically, let's just go through the math to make sure everything works out. Right here, cool, okay. So here's the same problem. We have a quarter circle of charge with radius r, and the segment is uniformly charged. So our first step, whenever we have just some arrangement of charges, is to use Coulomb's law, because Coulomb's law, it works for any dimension. In this case, we're using a one-dimensional object because charge is distributed along this line. So even though it's in the y-x plane or in the xy plane, which is a two-dimensional space, charge is still distributed along this line. The line is curved, but it's in one dimension. So we're going to use the one-dimensional form of Coulomb's law. Coulomb's law on our equation sheet reads the differential electric field is equal to k dq times r vector over r cubed. What changes by virtue of this being in one dimension, for this being a one-dimensional charge distribution, is the dq. So in one dimension, I did things in a different order here. Right here, just to be consistent. So the charge quarter circle is a one-dimensional charge distribution. And whenever we have a 1D charge distribution, dq is always equal to lambda dl. We're given lambda as just some constant. And dl, anytime I have a circular segment, dl is always going to be r d theta. So we can immediately figure out that dq is nothing more than lambda, our charge density, times dl, which is r d theta. So we already have something figured out. We already have dq knocked out. K is just a constant. But now we have to figure out what the r vector is, and then by extension, what the magnitude of the r vector is, such that we can finish up this problem. All right, so the r vector, it always points from the source to the observation point. So for instance, in this problem, my source is this quarter segment of charge. That's where I have sources of charge. And my observation point is the origin. So my r vector, if I draw an example r vector, actually let's use a different color. Let's use red. My r vector is going to point from my source to my observation point. And I like to always do this in terms of coordinates because it's a general approach that always works. So the coordinates of my origin are just going to be 0, 0, because it's the origin. And then the coordinates of my semicircle, well, it's along a circular arc. So I can say that the xy coordinates of any point along here, it's going to have some x coordinate and some y coordinate. But since it's just along a circle with radius r, I can say that the x coordinate is r cosine theta, and the y coordinate is r sine theta. That's pretty much just true for any circle whose angle we measure from the positive x-axis. So let's see. Yeah, xy we can say is r cosine theta, r sine theta. So then the r vector, because it's pointing from the source to the observation point, we take these coordinates and subtract the corresponding xy. So I'm going to have 0 minus r cosine theta for my I hat component, cosine theta I hat, and then I'm going to have 0 minus r sine theta for my j hat component, which just leaves me with negative r cosine theta I hat minus r sine theta j hat. And for its magnitude, I just take each component, square it, add them together, and take the square root of all that. The nice thing is that this is true for any circle. It's sort of like the definition of a circle. It's all points equidistant from one spot. So it just happens to be that all points along this semicircle are equidistant. And in fact, that distance is r from the origin. So the magnitude of my r vector, even without doing any math, is just going to be r. the radius of the circle. Cool. So that gives me little r, or that gives me little r in this equation, which is equal to big R in the problem. And that gives me the R vector, which is this right here. Let's see, any check. Oh, there's chat questions. Yeah, I've been I've had a lot of practice to do with the mouse this semester. Cool. So the bulk of the problem is done, I feel like. I feel like once we have Coulomb's law set up, that's the most difficult part knocked out of the way. All that's left is to just do some math, some plug and chug math. So we plug in what we found for dq, which is lambda r d theta. We've plugged in what we have for our r vector, which is this big expression here. And we plug in what we have for our little r, which is just big R. And because the problem is asking for these in terms of components, it's asking first for the horizontal component and then the vertical component. A logical way to split these up would be to just split them up at where I have the I hat and j hats. So I could split this into an x coordinate, or rather not an x coordinate, but an x component of my differential electric field and a y component of my differential electric field, d e sub y. All I did was distribute this expression into here and write everything out such that I have an I hat component and a j hat component. Cool. And it's asking for, whoops, not that. It's asking for the horizontal component first. So I am going to look at the x component. And I need to integrate it. So this is my x component of my differential electric field. And notice the thing I'm integrating with respect to is theta. I have a d theta here. So when I put this in an integral, the bounds of integration should be from wherever theta starts to wherever theta ends, because theta is what I'm integrating with respect to. So theta, in this case, starts at negative pi over 4 and it ends at pi over 4. Oops, wrong thing. So those are my bounds of integration. K, lambda, and r, those are all just constants. So I pulled them out. And I already set up the y component too, but it's a similar process for the y component. I just, instead of using this, I use that. And that's the different one. So let's make sure that we get what we want. So for the y component, whenever the sine function, so with the y component, I'm integrating sine of theta d theta. And if I draw out a sine function, it's going to look like this. And I don't know if any of you heard this terminology in calc or somewhere else, but sine is called an odd function because it's symmetric about the line y equals x. And one property of odd functions is that whenever I'm integrating across a symmetric boundary that's centered on the origin at x equals 0, or I guess theta equals 0 in this case. Because it's symmetric from its left side to its right side, so it'd be from negative pi over 4 over here to pi over 4 over here. I have as much negative area down here as I do positive area up here. So when I add those two, I get 0. So that solves one of my questions. It was the vertical component, and we figured out that it was 0. Let's see if that's correct. It is. Now let's figure out what the horizontal component is, or let's match it to one of these answers. The horizontal component is going to be negative k lambda over r, the integral from negative pi over 4 to pi over 4 cosine of theta d theta. And I don't think that's any of these, because this one's closed, but it has an r squared. This one has a theta in front, and so is this one. So none of the above. Cool. It's always frustrating when problems don't give you the right answer because you don't know if you did them wrong or did them right, but there's the solution. Any questions there?
This might be a very simple like circle question, but could
Yeah.
you go over how we changed dq in the like super original DE equation to lambda r d theta?
For sure. Let's reload this so all the junk goes away. And then the problem was called quarter circle. Where'd it go? Here it is. So this is the DQ that we started with, and it's the same one that appears on our equation sheet. If I pull up the equation sheet, it's right. Oh man, that's kind of blurry. There we go. It's right here for Coulomb's law. And we want to figure out how can we express that in terms of something that we can integrate. Because dq, it's a differential variable, and I can think of finding total charge as just integrating dq. But how do I integrate dq? What do I plug in for that integral? It doesn't make too much sense. Usually actually, I think I can say certainly that we almost always, when we actually do math, we're integrating either with respect to time or space. So how do we get these in terms of spatial components, basically? And the relationship that we want to use there is that dq for a one-dimensional charge distribution is going to be equal to lambda times dl. So lambda, if I think about the definition of lambda, it's just linear charge density. So it's a total charge over a total length. So if I go to the differential case, that same statement holds. Lambda is just some differential charge over some differential length. Or rather, if I want to solve for dq, dq is just going to be lambda times dl. And as far as dl, where that comes from, I said that dl for a circle is always equal to r d theta. The way I like to think about that is sort of just going back to probably pre-calc when we learned about arc length. And in particular, arc length is equal to just r times theta. So like if I have, in this case, my arc length would be, actually, let's undo that one. In this case, my arc length would be my radius, which is r, and then it spans pi over 2, because 45 plus 45 is 90, which is pi over 2. So that's my arc length. Just sort of a simple application of that formula. But that's not important in this problem. What's important is finding our dl. So if arc length is r d theta, it has to be the case that differential arc length is r d theta, because r never changes for a circle. Again, circles, the defining property of a circle is that it's equidistant from one point, and that distance is the radius. So r has to stay the same. What changes when we go to the differential case is that differential arc length is r times d theta.
Okay, I got it down. Thank you so much.
Of course. Anything else? Great question, by the way. Awesome. Let's do a Coulomb's law problem. And I'm going to pull from, yeah, I answered it. I'm going to pull from the same practice test, from fall 2017 on the final exam sections. And it's the very last problem. It's called non-uniform Q density cylinder inside, which is not the best title, but whatever. Let's zoom in so you guys can see it. So a very long cylinder with radius r, length L, and volume charge density rho equals rho naught r to the n, where rho naught is positive and n is also greater than 0. Yeah, positive, is shown in the figure below. Find the magnitude of the electric field inside the cylinder. So there's a couple of clues here that I want to use. Oh, there's questions. Yeah, cringe.
No, there's not. This is something we noticed.
That's been a problem for a long time. It's been a meme. There's a couple of clues here that are pointing for us to use Gauss's law. And the first clue is very long cylinder. So again, Gauss's law, I think we said this in the block 1 review session, but Gauss's law is true all the time. It's always true that whenever I enclose some charge, or whenever I have a closed surface, the charge enclosed is going to be proportional to the flux. That's always true. But it's only useful in finding the electric fields if I have symmetry. Basically, if two symmetry arguments are satisfied. First off, I have to be able to conclude that the electric field is parallel, to my dA vector. Because if the electric field is parallel to dA, then the dot product of two parallel vectors is just, I multiply their magnitudes. So I have E times dA. And then the next symmetry argument that has to be satisfied is E has to be uniform all along the Gaussian surface. So if E is uniform, then it just comes out of the integral. So I have E times the integral of dA, which is just equal to E times A. Those are the two symmetry steps that we always have to use in Gauss's law in order for us to use Gauss's law to solve for electric fields. And if you remember all the way back to block 1, I know it was a crazy long time ago, but cylinders are one of those 3 cases in which those symmetry arguments are satisfied. Because if I have a cylinder, technically it only works for infinite cylinders, but very long means almost infinite. If I have a cylinder and I enclose it with, let's say, this red Gaussian surface, and it's creating E field lines outwards, first off, it's going to be the case that along the sort of like shell of the cylinder, the electric field is uniform. So we're going to be able to pull E out of the integral. And second of all, the dA vectors of this Gaussian surface are also pointing normal and outwards of the surface itself. So E is going to be parallel to dA. The other 2 cases where we can use Gauss's law are going to be for spheres, because I could have, again, a sphere that's creating charge that goes outwards, and then the dA vectors are outwards. And I can have just flat planes. If I have a flat plane, then the electric fields are going to be going out. So I can just use any sort of Gaussian shape that I want. Cool. But we're dealing with cylinders here, and we need to find the electric field inside the cylinder. So let's pull that up. Load. I think it was the last problem. It was. Okay. All right. So again, a very long cylinder, radius R, length L, and volume charge density rho equals rho naught R to then, is shown below. And we're going to be using Gauss's law. Gauss's law on our equation sheet reads the integral of E dot dA equals Q enclosed over epsilon naught. And what we're doing, this is our cylinder, but we want to find the electric field inside the cylinder. So what we need to do is create a Gaussian surface that has a radius, whoops, undo. Oh, let's rotate, not undo. Oh, geez, where'd it go? Yikes. Whatever. Where was I? Shoot. There we go. Now we zoom in. What I need to do is to draw a Gaussian surface that has a radius smaller than the radius of the cylinder, because I'm looking for an electric field inside the cylinder. So that's going to be my Gaussian surface, and it's going to have a radius of little r as opposed to big R of the cylinder. Cool. All right, so what I always like to do with Gauss's law problems is to start by finding Q enclosed. I feel like once I have Q enclosed, the rest of the problem sort of flows from there. And to find Q enclosed, I am going to go, so the last problem I worked through, it was dq is equal to lambda dl. That was for a 1D charge distribution. But for Gauss's law problems, it's almost always going to be a 3D charge distribution. And that's certainly the case here because I have charge distributed within a volume. So I want to use the three-dimensional analog to this equation, which is dq is equal to rho times dv times the differential volume. We are given rho, we're given a function for rho, and we're not given dv. We're almost never given dv, so we have to solve for dv. The volume that's in question, though, is a cylinder. In a cylinder, the volume of a cylinder, I like to think of it as just, we have the area of the base, which is pi r squared. Then I multiply it through by the height, which is just going to be L. That's sort of a crummy cylinder, but whatever. So to find my differential volume, or my dV, I just take the formula for the volume of a cylinder, and I take a derivative with respect to r. So if V is equal to pi r squared L, dV is, I guess, dV over dr, the derivative, is going to be 2 pi RL. And then to get dV by itself, I just multiply over by dr. Cool. So now I have my two pieces for my Q integral. I have rho, which was given, and I have dV, which I solved for. And let's zoom in a tiny bit. Too much. The reason why I put primes on these r's is to just distinguish it from the little r of the Gaussian surface. That's what I'm integrating to. Again, if I go back to the picture, I'm only trying to find the charge enclosed within this Gaussian surface. So within, why isn't it highlighting? Oh, shoot. Within this Gaussian surface here, I'm only trying to find charge enclosed there. So when I go to integrate my Q expression for charge enclosed, I don't want to integrate to big R because that's the radius of the cylinder. I want to integrate to little r because that's the radius of the Gaussian surface. That's nested inside my big cylinder. So that's my upper bound of integration. Again, these little r's with primes on them, those are just to distinguish it from the r of the Gaussian surface. It's not that prime does not mean take a derivative. But regardless, 2 pi, L, and rho naught are all constants, so they come out of the integral. And then I have r to the n and just r. So when I have two of the same variables and they're both being exponentiated, I can just add whatever is in the exponents. So this has an exponent of 1, and this has an exponent of n. So I'm going to have 1 plus n over here. And then when I go to take a derivative, sorry, an integral, I increase the power of the exponent by 1, so this becomes 2, and I divide by whatever the new exponent is. So that's my integral. Let's see, any questions so far? Cool. How's that all sound for Q enclosed? Any questions there? It's been a crazy long time since block 1, and I know it's sort of an involved process, so it's perfectly understandable to be fuzzy on this. Awesome. Awesome. So that's Q enclosed, which is pretty much gets rid of or takes care of the right-hand side of Gauss's law. So now we need to do the left-hand side of Gauss's law. And the left-hand side of Gauss's law, again, we already argued that the electric field points radially outwards from the cylinder. This should definitely be a dA. So E and dA are parallel, so that's our first symmetry argument satisfied. That's how I got rid of this dot product right here. And then E is uniform across the Gaussian surface. So because it's uniform, I can pull it out of the integral, and I have E times the integral of my Gaussian surface. So again, Gauss's law, I'm always integrating over my Gaussian surface. So the area that I consider here, the area on the left-hand side of Gauss's law, is going to be the area of that cylinder. It's not going to be the big cylinder that actually carries the charge. It's going to be the little cylinder nested within that is my Gaussian cylinder with radius little r. That's what I'm integrating over. And accordingly, its area is just 2 pi RL. Cool. So now I have everything put together from Gauss's law. I have the left-hand side and I have the right-hand side. So now I just need to solve for the magnitude of the electric field, which means divide by L. So those cancel, which is good because I wasn't given L. The 2 pi's are going to cancel. And this R is going to cancel with one of those there. That's just going to become a 1. So I'm left with that. E is equal to rho R to the 1 plus N over 2N epsilon naught. Let's make sure I got that right. I think it was that one. Yeah. Yeah. Cool. Any questions? Oops. I don't see anything in the chat. Awesome. All right, Tyler, what are you thinking for what we do next? Should we go to block 3 stuff or should we go back to block 4?
Yeah, I'm thinking just because block 3 was there was so many responses that wanted to see those. I think just maybe one problem from that, or I mean, I guess maybe 2. It depends. Doesn't matter to me, whatever you'd like to do. But block 3 definitely seems like is a one that people would like to see.
I can definitely grab a problem. The bunch of notifications you got were for work problems there. So if you want to choose something else,
Gotcha.
Yeah, for sure.
I realized that after.
Yeah,
Go right
yeah.
ahead.
Let's see, what is there from block 3? Let me do the same thing and we'll sort of probe everyone to see what's most in demand. We can do an Ampere's law problem. So I'll say that's option 1, Amperes. We can do a Biot-Savart law, BOS. We can do just a flux problem. Flux. We can do a forces problem. There's a bunch of those. And I think all that's left after that is just Faraday's law. Yeah, so block 3 was pretty big. There's a lot to choose from, but I don't know what people want to see. So let's see what's in the chat. Ampere. We can definitely do the diamond refraction afterwards. Does the line integral of dA always result in surface area of the Gaussian surface? So you can't take a line integral of dA, but I'm assuming that was just a typo. You can take an integral of dA, which is always going to be the surface of the Gaussian surface in Gauss's law problems. Yeah. If that's what you meant, James, by line integral. Because line integrals you can only take over when I'm integrating with respect to DL. For surface integrals, it's going to be, okay, cool. Tyler, looking at the chat, there's at least 2 people who want to do block 4 stuff first. So if you want to,
Sure. Yeah, there's not
maybe,
too many.
Maybe do diamond refraction first, and then we'll come back to block 3.
Yeah, diamond refraction will take all of 5
If,
minutes, so no worries.
I feel like block 3 is pretty fresh in everyone's minds. That's why it's not.
Okay, guys. Yeah. So the problem Lisa's talking about is in the 2017 final exam folder. It's actually the second to last problem called diamond refraction. Share that real quick. Ready? Yeah, we got that. Perfect. All right, so I'll write out again just what we're doing here. We're in the 2017 set. All right, we're on the diamond refraction problem, again at the very, very end almost. Cool. So my art skills are really not great, so I'm not gonna draw a diamond, but there's a very nice picture of a diamond, basically what's going on. But so it says, diamond not only has a high index of refraction, but also has a great deal of dispersion, meaning the different colors of light see different indices of refraction. Interesting. Red light, for an example, sees an index of refraction of 2.41, Blue light sees an index of 2.45. All right, so we know that different indices mean different amounts of bending, meaning the colors get separated in the gem. Right, that gives the diamond its characteristic color sparkle. Right, also kind of a callback to what I was talking about earlier. So good stuff. So we want to know if light containing a mixture of blue and red light enters a diamond at some angle, right? Obviously yours will be different with respect to the surface normal. The blue and red light will separate. What will be the angle theta d in degrees between the two rays in the interior of that diamond? Right, so I won't draw the whole diamond, but I will draw the top here and what we're actually talking about. Right, so got our normal here. Right, we're saying our first wave, which is some mix of blue and red, which if I'm not crazy is purple, I think. All right, so I'll do that, right? Some mix of blue and red, right? At that theta incidence angle, right? Which that gives it to you, right? So theta in going to be theta 1, we know, because we're going to use Snell's law, right? Is going to be, for me, 24 degrees, right? And then because diamond has a great deal of dispersion, right? Meaning that, like I said, different colors of light see different indices of refraction. Really, what's going to happen is when we go in here, red and blue are going to be separated by some distance, or some angle theta, I should say. Right, so that's our red, and that's our blue, for example. Right, both these angles are measured to surface normal. Right, so that's theta. I'll call it theta b. Right, and then we have theta r. Right, for that angle. Right, and what we're asked for is the angle in degrees between the two rays. Right, so really what we want. Right, that was just a random guess, as if red is bigger than blue. I have no idea. Right, but really, what we want is the absolute value. Right, I'm pretty sure red is always bigger than blue, but what we really want is the absolute value between the two. Right, we'll call that our theta, just theta by itself to find the answer there. Right, so that's what we're looking for. Right, we know that there's different indices of refraction, right, and we know that we're going to have two different refraction angles. Right, so we just want to know what the difference between those two angles is. Right. So as you might have expected right now, we definitely want to do a Snell's law problem, right? Or Snell's law setup, I should say. Right, so I'll have red right here. I'll say N1 sine of theta 1 equals N2 sine of, I'll call it theta r again. Right, and then we're going to have a similar thing for blue. Right, N1 sine theta 1. Right, or again, they both enter the diamond at the same angle, right? Because we have purple, which is some mixture of light and blue, or red and blue, I should say. Right, equal to N2 sine of theta b, right, for theta blue. Right, and so just to make sure there's no questions, there's none. Good, good, good. All righty, yeah. So like I said, we're asked for the difference between those two. Right, so the problem's fairly straightforward. Right, all we have to do is solve for each angle and then take the difference between the two. Right, we are given the index of refraction for red and blue individually. Right, so I'll say NR is going to be, I believe it's 2. Let me check just to be absolutely sure. I believe it is 241. Right, and blue is 2.45. Right, where those are equal to N2s in both cases, right? Because that is the index of refraction that light experiences, right, once it is dispersed inside that diamond. Right, so from here, right, we know that it enters from air, right? So that means N1 in both cases is going to be 1. Right, so I'll just say N1 in purple, right? It's just equal to 1 because that is the index of refraction of air, right? And I'm going to rearrange to solve for each one. Right, so theta r, right, is becoming the inverse sine of N1 sine theta 1 over N2. Right, and for blue, that is exactly the same case. I will copy it down here. So I will change it to our blue to be consistent. Right, and I will find out what both of those angles are, right, just in terms of numbers. And obviously mine will be different than yours, so I won't even bother calculating them. Right, we'll get two different numbers there, and all I have to do is take the absolute value of the two, right, or the absolute value of the subtraction of the two of them. Right, and that's how I would find the distance between those two refracted rays, or the distance, and the angle between the two. All right, I feel like that one's fairly straightforward once you realize what the problem is even asking for. Right, that's the most difficult part, realizing it's asking for an angle between two rays as opposed to just an angle by itself. Right, and I guarantee you on a multiple choice question, these two would have both been answers. I guarantee it. Whatever that angle was and whatever that angle was, those will both be answers. Right, so just make sure you read the problem carefully, right? Because that's really one of the only ways we can make it more difficult on you. right, so any questions about that one? I know they're like I said, Snell's law problem is probably pretty fresh in everybody's minds, right? So I don't expect there to be any questions, but if there is, feel free to unmute or type something in the chat. But if not, Nick, I will pass it back to you. It looks like that's what we have time left for.
Sure, I can do a block 3 thing.
Yeah, I feel bad, man. All the block 4 stuff is fairly straightforward
No,
compared
you're
to
good. No,
the
you're good.
involved problems you've had to do.
I like block 3. I don't know. There's so much to choose from, and I haven't really gotten anything from the chat yet as to which kind of a problem. So I'll just ask again. What problem do people want to see from block 3? I can do Biot, I can do Ampere, I can do a magnetic force as one. Faraday's law. Any thoughts?
Yeah, the second time we've seen an Ampere thing. I think
Okay. Yeah, let's do it. Ampere. Let me find a long kappa problem on Ampere's law. Give me 1 second. Sorry, should have had it ready. My bad. Block 3. Let me start sharing so that people can see long kappa.
Nick, there's one called non-uniform current density in the 2017 set.
2017. Non-uniform.
I was talking about the final exam stuff, but I don't know.
Okay.
I don't know if it's there or not.
Non-uniform current density. Where'd it go?
Yeah, about halfway there.
Found it.
Yeah,
let's see. Do I have that one worked out?
It looks familiar. You might.
Because I have like a billion problems here. Not seeing it. Oh, here it is. Cool. Yeah, awesome. Let's do that one. I like that problem. Oh, too big. There we go. So let's go back to long kappa. All right. So the figure shows the cross section of a hollow cylindrical conductor with radii A and B, which has a current density J equals 7R squared over its cross-sectional area. So that means over this gray section here, where J has units of amperes per meter squared. Find the magnitude of the magnetic field at a distance of 2.3 centimeters from the axis. Okay, so what this problem is telling us is that we have an inner radius A, that's A, an outer radius B, where A is 0.7 centimeters and B is 4.2 centimeters. And they want the magnetic field at a distance of 2.3 centimeters. So they want the magnetic field, let's say at a distance R, where R is between, scroll down. Whoop, oh, that messed it up. Whatever. Where R is between A and B, sort of at that radius right there in between the two. And since this is an Ampere's law problem, that's going to be my Amperian loop. Wherever I want the B field, that's my Amperian loop. So let's start by writing out Ampere's law. Now I clear it. There we go. So we can use Ampere's law to solve for the magnetic field since we have nice cylindrical symmetry. That's pretty much the only case when we use Ampere's law. Like with Gauss's law, we can use it with cylinders, spheres, or planes. Ampere's law, we can pretty much only use it with cylinders. Technically with solenoids too, but I don't think we derive that ever. The equation's on the equation sheet. Cool. So that's our general expression for Ampere's law without a displacement current, but we don't need it here. And kind of like with Coulomb's law, where it's easiest to start with the right-hand side and figure out what the charge enclosed is. For Ampere's law, I find it convenient just to start with the right-hand side again and solve for I enclosed. And the most general expression for I enclosed is going to be the integral of J dot dA. So J, if you remember from block 3, is the current density. That is basically the current per unit area. Or that's what it would be if the current was uniform. So if I had just like a wire and current was coming out of that wire, the current density would be what my total current is divided by my cross-sectional area. It's usually for wires, the cross-sectional area would just be a circle. I over pi r squared. But that's not the case here. In this case, we're told what our j is. We're given a function for j. Our current density. So that's given as a function of r. So then all that's left is to find what dA is. And dA, well, if current density is the current that's going through a cross-sectional area, sort of like the current per area, then we need to consider the area, the cross-sectional area of the wire. And we're dealing with circles here. So even though we do have this sort of crazy setup where it's like a tube rather than just a plain circle, we can still say that we're integrating over a circular area. So our area is still pi r squared, which means dA is 2 pi r dr. Again, if I just take a derivative of a with respect to r, I'm going to get 2 pi r. So then I move the dr over. So just to say that more clearly, I don't think I said it well the first time. We are trying to find the current going through my Amperian loop. So if I draw my Amperian loop here, since it's between A and B, I'm trying to find the current enclosed in that Amperian loop. So I'm trying to find everything here. Everything that's in the wire section, or in between A and B, but not smaller than A because, well, there's nothing smaller than A because A is where the current stops. So I'm basically just trying to find current in that section. And to do that, I'm going to have to integrate my J, my current density. And since I'm integrating over a circular cross section, my differential area is going to be 2 pi r dr. Cool. Any questions so far? Doesn't look like it. So if I set up my integral, I through is going to be the integral of j dot dA. And in this time, my bounds of integration are going to be from A to R. So I don't want to integrate from 0 to R, first of all, because I can't. If I try to integrate, shoot, can I? I can, never mind. There are some problems where the current density J is given as 1 over R squared. I think I was thinking of one of those problems. If I try to integrate 1 over R squared at the origin at 0, it diverges there, so that integral isn't defined. But here I can. But regardless, you shouldn't, because that's not where the current is. The current is going through sort of what I drew earlier. It's going through this orange section that's enclosed by my Amperian loop. And that Amperian loop, even though it's sort of with reference to the axis, sort of at the cylinder there, or at the center there, the current doesn't actually start until I reach a radius of A. So that's my lower bound of integration. So I'm integrating from A to my Amperian loop R. My current density is given as 7. I just called it alpha for some constant. 7R squared. Again, the R just means to not confuse it with this R of the Amperian loop. And my dA is 2 pi r dr. 2 pi and alpha, and in my case, 7, I think was the constant they gave me. Yeah. Those are constants, so I can pull them out of the out of the integral. There we go. And I'm left with the integral of r cubed dr, which is going to be r to the 4th over 4. So when I plug in my bounds, it's going to be r to the 4th over 4 minus a to the 4th over 4. Any questions on I through? Awesome. So that gives me the current going through my Amperian loop. That gives me the current in the orange section there. But I still have this left-hand side of Ampere's law I have to deal with. But thankfully, the symmetry arguments are going to be the same pretty much anytime I can use Ampere's law, because I have this Amperian loop. Actually, to be consistent with my earlier picture, let's make the Amperian loop blue. That's my Amperian loop. And I have magnetic field going tangential to that loop. So sort of by analogy to block 1, where we have Gauss's law, and we needed to satisfy symmetry arguments to pull E out of the surface integral there. In block 3, we have Ampere's law, and we need to satisfy symmetry arguments to pull B out of this line integral. But the symmetry arguments are pretty similar. Again, B has to be parallel to DL, and it is, because if these are my B field vectors, those are going to be parallel to DL, which is always just sort of tangential to a circle. So those are parallel. And because my Amperian loop is centered on the wire, B is going to be uniform along that Amperian loop, so I can pull B out of the integral further. What I'm left with is the integral of DL, which is just the length of the Amperian loop. That's going to be the circumference of it, 2 pi r. Cool, so I have Ampere's law all set up. The left-hand side is the integral of B dot dl, which is 2b times 2 pi r. And then on the right-hand side, I have mu naught times I through. And when I divide by 2, the pi's are going to cancel. The 2 is going to become a 4 over here. And then I also have an r from the left-hand side. So this is what I get for my final answer. Any questions there? Awesome. Awesome. I can do another block 3 question if you want, Tyler, or if people want, I guess.
Yeah, I just want to say, guys, that's the end of the scripted material
Yeah.
we had anyway. Obviously, if you want to see it, that's more than fine by us. We're more than happy to keep answering some questions for you. But before most of you guys jump ship, we just want to thank you guys for joining us for these this semester. They aren't required by any means. Nick and I just really enjoyed doing them. So it means a lot to us when people actually show up and are engaged a little bit. So we thank you guys for that. Other than that, you're quote unquote free to go, I guess. But yeah, we're more than happy to sit here and answer questions if you guys have any more. Feel free to drop them in the chat or unmute yourselves. That's totally fine. But like I said, thanks again, guys. We really appreciate it, and good luck on your final.
Yeah, just to beat that drum one more time. You guys make it worthwhile for us to do these, so thanks for showing up, and hopefully they've been helpful. And it's been a great semester. It's been a great semester. Man, they're dropping like flies.
Can't blame them, man. They got a lot of
Yeah,
finals.
no, I don't blame them either.
Yeah, you're welcome, guys. Thanks again. Take care.
How about question 21 on exam set 1? I can do that one.
Yeah, sounds good. Question 21 on exam 1 set. I figure out what that even is.
There are 21 questions. Are there? Oh, I see. Block 1 exam set.
Oh, just like the actual exam?
I don't know. Can you clarify what you mean by that question, Sebastian? Or not Sebastian, James?
Yeah, Nick, go to the exam 1 spring 21 folder, and it's actually just question 21. That's our bad. I forgot that those were posted.
Okay. I am in the wrong year. I'm in fall 2020 for whatever reason. So let me go back to this year.
Yeah, Nick, it's the like 2 sheets of charge thing that they always throw on the exam.
Gotcha. Okay. Let me share my screen. Cool. Hopefully they can see that. So we have 3 infinite sheets of charge with charge densities sigma, -2 sigma, and sigma placed in the configuration below. What is the magnitude of the electric field in region A? So in that region right there. All right. Why won't it let me? There we go. So it wants the electric field in that region A. And what's nice about infinite sheets is that the electric field from an infinite sheet doesn't depend on the distance from an infinite sheet. So if I look on the equation sheet, there's a lot of sheets in one sentence. If I look on the equation sheet, the electric field made by an infinite sheet is sigma over 2 epsilon naught. And nowhere here do I have any sort of spatial dependence. So I can be a mile or 10 billion miles away from an infinite sheet of charge. I'm going to be feeling the same electric field from that infinite sheet of charge. Which is nice because it means we don't have to really consider anything other than where region A is relative to the plates. So let's see, we have a positive sigma plate here. And then we have a positive sigma plate over here. Those two plates are going to cancel out because I have positive charges going, electric field lines always move away from positive charges. So I have electric field lines going away from this bottom plate right here. And I have electric field lines going away from this top plate right here. But since they're both going away from each other, those two outer sheets, both of charge density sigma, are just going to cancel out. So all I have to care about is this sheet right here, the -2 sigma one. And it's asking for the magnitude of the electric field. So again, if I look on the equation sheet, the equation is going to be E is equal to sigma over 2 epsilon naught. That was just taken straight from the equation sheet. Now, if I want to apply it to this problem, it's asking for magnitude, so I'm not going to worry about the fact that it's -2 sigma. I'm just going to pretend it's +2 sigma. But regardless, I have E is equal to 2 sigma. And again, distance doesn't matter, so I have over 2 epsilon naught. The 2's are going to cancel, so I have sigma over epsilon naught, which looks like is what it wants from me. That was sort of quick, but did that make sense? James? Cool.
All right, guys. Anything else? It's floor is wide open. If you have anything you'd like to have answered, please feel free to drop it in the chat or unmute. We're totally fine. Or I guess we could just end there, I guess. I mean, totally fine.
We sort of get that, not kicking anyone out inside, it's just understandable that it's finals week and everyone's busy.
Absolutely. It's our pleasure.
Yeah.
Have a good one. Cool. Well, Nick, looks like that's it, man.
Awesome.
That's all we got. Well, cheers, man. I will see you on Friday for the yeah, I'll see you on Friday for the final. I'll talk to you about something else later.
Okay. Take care.
You too, man. See you later.
Bye.